Hey guys, good evening. So we are back with our interview series, or rather, the series of videos for interview preparation. So the last few videos, if you have checked, you might have got, we have covered one stack question, one DQ question, and we had looked into a backtracking question. So you can cover those things because they are quite fundamental. And today we are going to see another problem, which is regarded as again one of the hard problems. And again, in terms of the, things that we use in that problem, it is quite fundamental for your interview preparation. Like it is not such that you cannot do without those topics, but for your overall confidence in the interviews, as well as to mark your preparation in front of the interviewer, an expertise in such topics will actually form a great difference. So when the interviewer finds that you know these things and you basically know how to apply these things and understand the problem and know how to approach it in that manner, it actually helps. It actually very strongly helps. So here we have one such problem, and we'll be looking into that problem. This is a slightly harder problem than the previous ones, but we'll look how we can solve it in different approaches. So whichever suits your interest, you can solve according to that. I will solve according to one particular interest, which I think will be convenient for most of you. So yeah, let's begin. And before that, don't forget to subscribe the channel and what else? Yeah, let us know about what videos you would like to have in the coming weeks, and how are you liking all of these things. Please share your feedback. I don't usually check them personally, but the team will convey to me whatever feedback is being obtained. So it shall, uh, actually drive us in the right direction. That what type of videos you actually require, will actually make that kind of videos. So about myself, I am Saptarishi Mukherjee. I am an educator at CodeChef and Unacademy. I have graduated recently from IIT Bhilai from the stream of Computer Science and Engineering. I have been a master at Code Forces and a six-star rated coder at CodeChef, and I've been to the ASEAN ICPC regionals in 2019, and I'm going to join Google soon. So that's about myself, and now let's come back to the interview question. Okay. This has been asked in many companies. Like this has been asked in the past in Google, Amazon, and many such companies. Netflix, I've actually forgotten to fetch the list, but yeah, these three, four names, which are giant names, I remember that they have all asked this question. So it makes sense for us to discuss this, right? Okay. The question goes something like this: that you have some kind of grid. A grid means basically you have some rows and columns, and every cell which is being created, all these cells are being created by horizontal and vertical lines, right? So in all these cells you have some values, okay, and those values can be both positive and negative. Those values can be anything. They can be positive or negative, or they can be even zero. So you have something like this, or we can imagine, let us imagine a shorter version. Maybe suppose 302 minus 1 4 6 minus 5 2, and in this way all are filled. And now suppose very large values are filled over here to 200, 300, all these things, large values are filled over here. And suppose I have asked you that you need to tell me one such rectangle. You have to find out such a rectangle. Maybe I think for the time being we can actually choose smaller examples. Yeah, so yeah, I think this would be fine for an example. Let us choose only this much. Okay, this is our grid, which has 4 columns and 2 rows. And we are asking that fetch us, suppose, a sum as much as possible less than equal to 10. Okay, so what can we see? We can see what are the ways we can do it. We have to use rectangle. So this can be one rectangle. If we choose this rectangle, we'll get a sum of 2. If we rather choose this rectangle, we'll get a sum of 6, right? If we choose this particular rectangle, we will get a sum of 6 plus, okay, this particular rectangle will get a sum of 6 minus 1, 5. And we can see if we choose this one, we'll get exactly 10. 5, 2 plus 4 minus 1 is 5, plus 3 plus 2 is 10, right? Now if we say no, we want 12. So what can we say? If the question mentions 12, Then we can do something. We can take this entire thing. What will this form? This will form 11. So 11, if we take the entire thing, I think it will form 11, right? 10 plus 6 minus 5 is 11. So we can say that the sum is quite close to 12. It is not exactly 12, but we don't have a candidate which is better than 11. We don't have exactly 12. So this is the best one. So you have to actually find the rectangle, or you have to find the maximum sum for any rectangle within this particular grid which is possible, such that the sum is closest to the target sum, that is k. Okay, so it cannot cross this k. So suppose you have been given k is equal to something, suppose 15, then you have to choose such a sequence, or maybe you have been given something like k equals to 6. Then you have to choose something like this, or maybe you can even choose this one, and you have to say, okay, it is exactly possible. But if you have something like 7, then you have to think what is the best you can form. Maybe you can try something like this. 6 minus 1 is 4, slightly lesser. 4 plus 6, it is 10 minus 1, again slightly more. 6 plus 6, 12 minus 5. Okay, here we are getting exactly this. Okay, so you can have this rectangle in any manner. There are some rows, there are some columns, and you have to find out the maximum sum of rectangle. And this is in terms of, like, you will find this is quite a classical question. This has become quite a classical question. Before interviews, everyone practices this, but it is actually a hard question. Or it's a medium hard question, we can say. It doesn't use us very complex things. It's a sort of medium hard question. Okay. In lead code, you will find this is a hard question. In interview bit, again, like it has been treated, I think, as a hard question. So anyway, it depends, but let us see how the two-dimensionality increases the problem, or whatever we have in this problem. Let us see. So first of all, you have got a grid. You have got this kind of a grid, and I hope the problem is clear. You have to find out what maximum sum you can choose by selecting a rectangle such that the sum does not cross your k, right? So you have to be very specific and formal. You have got some n rows and you have got some m columns. Okay, n rows of the grid, m columns of the grid, and you have so n can go up to, n is always positive, and n can go up to about 10 to the power 2, that is 100. N can go up to 100, m can go up to 100, and these values, whatever values are over here, ai, aj, or aij, you can say ith row and jth column, whatever they are. So for all I and j, basically we have aij less than equal to, we can say something like 10 power 3. Okay, what next? We know that k is less than equal to 10 to the power 5. Okay, so these are our constraints. These are the constraints which we need to keep in mind while we form our solution. Usually, according to the traditions, we have to form such a solution such that the number of operations is below 10 to the power 8. It is at most 10 to the power 8, or at most 2 into 10 to the power 8, not more than that. Right, so how can we approach this problem? The brute force. First of all, it is important that when you see a problem, you know how to form the first solution. Because unless you form the first solution, thinking about what is the best way in solving is just like, a haphazard method of first, climbing on DP and then on greedy or something like that. So you should first know how to form a first solution, and then you can think from there whether I can apply bit masking or DP or segment trees or something like that. Okay. So the first problem can be something like this, that okay, for any for any rectangle, what is the choice we are making? We are first making the choice of the range of the rows, right? We are making the choice of the range of the rows, and then we are making a choice of the range of the columns, right? So if suppose it is starting from R1 to R2, it has from R1 to R2, and it has from C1 to C2, what we can say is for all possible R1 and all possible R2, we will run it. So all possible ranges, what are the number of ranges? We can basically select how many? Out of this n rows, we can select how many rows? We can select the 2 rows in NC2 manner, in NC2 ways. Then we can select the 2 columns which can form the boundaries in MC2 ways. Okay, you can also think it in the form of your loops. They will also asymptotically come to the same thing, but this is the exact thing. You have n into n minus 1 by 2 into m into m minus 1 by 2, which is exactly order n square m square. Even if you think like a for loop, that okay, I'll run a loop from like I'll run a loop where the outer loop is going to contain which is going to be my starting row, next loop is going to contain which is going to be my starting column. For the columns we will again have similar to for loops. So this is what the for loops themselves involve. Now once we have this, what can we say? What is the time taken to form this? What is the time taken to get the sum of this part? What is the time taken to form the sum of this part? You have to multiply. So for every rectangle which is formed by taking this kind of, by playing this kind of combinatorics, by applying 4 for loops, whatever you are getting, you have to find the sum. Naive method is you calculate everything, and for that you basically have to multiply, you have to take into consideration all the elements, which can make it reach again another nm. But when you have actually come to attend this problem, if you are not sure how to get rid of this factor, I would say that pause this video for a moment and think about it, how you can improve this part. To improve this part, it is quite easy, and I think some of you may have got. You can use simple prefix sums. Here prefix sums also need to be used in two-dimensional order. How? We need to form prefix sums in this manner. Whatever we are getting up to here, we need to form prefix sums, and then for all of these we need to form the prefix sums in some manner like that, so that maybe something like this. Suppose over here, suppose you form prefix sums in all these elements. Over here, suppose you are storing what is the sum of elements up to here. Okay, you are storing what is the sum of elements up to here, and then for all the elements you have the prefix sum up to this element. Now what can you say? That let us form another prefix sum using these elements, whatever we have formed in this, which is just the prefix sum up to here. So this element is what is the prefix sum up to here. Now we will form prefix sum this side. We will go this side and form the prefix sums. So now what will this element, when we form that new matrix, what will this element tell us? This element tells us what is the sum of this one plus this one plus this one plus this one. The summations of all these things will be stored here. What will this particular value tell us? This particular value will tell us I'm sorry. What is the sum of this one plus this one? Suppose you have to find for this particular rectangle. Okay, so for this particular cell, you have found out what is going to be the prefix sums, what is going to be the sum of all these elements. So what can we say? Using this particular value, what can we get? The sum of all these elements, right? We can directly get this, and using this value we can get the sum of all these elements over here, right? So one part is becoming common. What can I see? That using this particular element we can get this part, which is this part initial, and using some such element we can actually get this part. So from this entire thing I need to minus this part. I need to subtract all these parts, but this part will get cancelled twice. So in order to bring back this part another time, this is inclusion exclusion, which is slightly advanced. But I think this particular example is not very hard. What I'm doing is I'm simply saying that, okay, suppose this is RC and suppose this is R dash C dash. Okay, suppose this is this has become quite dirty. Suppose it is okay, suppose this is R dash C dash. This particular guy is R dash C dash. What do we have over here? This is R dash C dash. So from here what can we say? This is going to be what? This is going to be R dash comma C, and this is going to be R comma C dash. Makes sense? So from here what can we say? The dp, the number of ways from RC, if we subtract the number of ways of or the sum in R dash C, and if we subtract the sum in R dash C dash, and if we add, I'm sorry, r and c dash, and if we add this part which we have excluded twice, that is r dash c dash, can we say that yes, now we have got this particular part only, we have got this particular part only. So you see, if we have to find from the rth one, or whatever way you can understand, right, from r dash to r and from c dash to c, if you have to find for this particular range, then you need to find out which is that diagonal cell which I'm targeting to eliminate from there. And from that particular values, from from those particular coordinates of r dash and c dash, you need to do this operations. Does it make sense? I'm sorry, I'm coughing a bit because yeah, recently I've just got some cold. But I hope it is clear to you, right? Cool. So what I basically meant to say is that using this basic prefix sums, just a second. Usually this weather changes are sometimes not so congenial. So anyway, what I'm trying to establish through this is, using this prefix sums or similar things, I can easily reduce it from order r square, order n cube m cube to order n square m square. I can easily reduce it from order n cube to order n square m square. Okay. This entire thing actually made it order n cube m cube. So I have been able to reduce it to order n square m square. How? Using some pre-computation. And what is the complexity of the pre-computation? Again, it is the same thing, order n square m square. Okay. So using this, I know that, okay, I can code this solution. I can code this solution and I'll be able to get something, because if you are able to code this, you are like, at least the interview comes to know that you know DP, you are not afraid of 2D things. These are the things that the interviewer comes to know. So it is important that you are comfortable with at least the basic, approaches, if not the best approach. Okay. Now the thing is, how can we do better? It is something like this. Let us see where we are doing worse. Just like my previous videos, that is what I'll be targeting on. Where am I doing worse? How can I better that? So I think this is where exactly we are doing worse. Tell me whether it is so. I want to find, suppose I've chosen the rows. Okay, I've chosen that this, for this row I'm going to check. Now I'm going to find out for all the pairs, for all the columns I'm going to find. Can I say that since I have visited all these columns, when I'm at this column, if I have the prefix sum, which basically indicates the sum of all these elements, and I have all the previous prefix sums, I have suppose all the previous prefix sums, what can I say? That this prefix sum in red minus this prefix sum in green will give me the answer for this part, right? So what I'm saying is that if I have the prefix sum for this part and if I have the prefix sum for this part, where prefix sum means I'm talking about that I have taken these two rows into consideration, whatever values I'm getting, first this is the first value, okay, the sum of these values is my first value, the sum of these values is my second value, the sum of these values is going to be my third value, whatever sum I have over here. Okay, now what can I say? If I use this value and if I subtract this particular value which I have maybe somewhere over here, I will get the remaining part. So if I have all these parts, can't I make a smarter choice? Because I know what is my target. The target is not a very random thing for me. Can I make a smarter choice to say which thing? So what I'm trying to say is, suppose this particular thing, suppose this this is J, okay, this is column J, this is column J, the last column that we are taking. So prefix of J indicates the summation and summation of, suppose the starting row is R1, R2, so R will start from R1, it will go up to R2, and J will start, or suppose something K is going to start at 0, the first column, and it is going to finish at J, and we need to add all the values A of R, K, okay, let us mention it as C, okay, let us mention it as C. So for all these columns 0 to J, I'm going to store this. Got it? So what am I going to show? This is basically what I mean by the prefix sum. So if I store this, what can I say? That this part, if I have to represent this part and I know that this is basically C1 and this is C2, what can I say? The answer is basically pre of C2 minus pre of C1. And I know that this particular value has to be less than equal to k and the best possible value. So this should be the shortest value. If I'm choosing that it should end at C2, then I should choose such a C1 that I'll get the best value such that the difference is less than equal to k. Does it make sense? Okay. So this is still brute force for me. R1 and R2. I will say, okay, choose all possible R1 and R2. Once you fix the R1 and R2, form this. Okay. And now I want to choose this best thing. Again, you can use the prefixes which we discussed earlier for your optimizations. But try to understand first the approach that I'm going. Optimization will be easy. Everything can finish in order n square m square. But the thing that I'm going to say is, what we are currently doing is, we are considering all possible subarrays. Ending at C2, we are considering this subarray, we are considering this subarray, we are considering this subarray and all possible subarrays. Is that really required? I don't think. If we have all the prefix sums, can't we choose something? Based on this value, the prefix sum, I know that the prefix sum, this C1 we don't know what is the best C1 for a particular C2. I can say this has to be greater than equal to pre of C2 minus K, right? We can say something like this. Pre of C2 minus K, this has to be like, it should be greater than equal to this. And I know it should be as small as possible. Okay, it should be as small as possible. Why? Because this greater than equal means I am reaching the threshold and I have to do something just the opposite. I should not cross it, but I should reach as close as possible. So this has to be as close, as minimum as possible, but greater than equal to this, right? If you think about it, this is basically what we get. So can't we use some structures? Because we basically have to find such a C1. Suppose I reach this C2, I've got the prefix sum value. I have the prefix sums for all the previous ones. I have this value for all possible C1. Okay, I have this particular value for all possible C1. Again, I have fixed this R1 and R2. For this, I'm talking about all these prefix sums. So when we know this, what can we stretch from here? Can we say that if we have some sorted structures, we can easily do some binary search kind of things? If we have some sorted structure, we can easily do some binary search kind of things. What are the things that are possible? Now, we cannot say that just sort all these pre-Ci elements. Just sort all these elements, we cannot suddenly say. If we sort all these elements, and if we say, okay, we need to choose now a difference between any two. We don't know which, like we should choose such a thing such that C2 comes after C1. C2 should not come before C1. You cannot choose C2 over here, C1 over here, and you cannot say that C2 minus C1 will give me the value. Then we'll get negative of the sum, right? We should not choose that. So definitely there are certain things which need to be kept in mind. But we understand that, okay, before visiting this C2, if whatever prefix sums we are getting up to this, if we sort them, then we can find the perfect place for C2. That is, which is the perfect candidate from these available sets, which if I choose as my predecessor, is going to give me the best value. That is, which is the rectangle formed between the rows R1 and R2 that ends at C2. So I'm basically solving this question and I want to solve this question optimally. That which is the best rectangle ending at column C2 starting at row R1 ending at row R2. Yeah, these are the things. Best rectangle means we know what we mean by the best rectangle. It should have the best sum such that the sum is not greater than k and it is the best possible, the maximum possible. So if we have fixed the ending column, if we have fixed the starting row and if we have fixed the ending row, ideally the C1 can be anything. So the knife time complexity is basically order C2, or we can say it is going to be order m, because C2 can be at most order m. And even if we say order C2, then also the average time complexity will come out to be order n, because average time complexity, like average value of C2 is n by 2. So n by 2 is order n. Keeping all of these things in mind, Can we have a better approach? The thing is that before C2, whatever prefix sums you have got, you can arrange them in a certain manner so that you can choose the best value. Suppose you arrange them in a sorted array. So they are sorted. So you find out, yeah, C2, which is the best element, you have found that out. Now you have to include C2 over there, right? So that for the next person who is C2 dash maybe, for that next person, when we are searching the previous, best column, you can again get a sorted array. So what is the cost of introducing one element into a sorted array? Can you recollect insertion sort? So if you use insertion sort over here, this is going to take order n time, order m time, right? So definitely, like over here, our searching can take place in log n time. Our searching can take place in log m time, but the placing of this element so that the next column can actually find it congenial will take again order m time. तो कुछ ऐसा है कि हमारे एक कॉलम को फाइंड आउट करना है कि मुझसे पहले जो भी कॉलम तक हमने प्रीफिक्स सम देखा है, कौन मुझे सबसे बेस्ट डिफरेंस दे रहा है। मैंने वो तो फाइंड कर लिया क्योंकि वो सॉर्टेड है, मैंने मान लिया। अब मुझे वापस इसको इंक्लूड करना पड़ेगा क्योंकि मैं नेक्स्ट कॉलम में जा रहा हूँ। नेक्स्ट कॉलम में जाके मैं सेम क्वेश्चन पूछूंगा कि अब मेरे पीछे कौन सा बेस्ट है। वो जो मैं अभी जिसके रिस्पेक्ट में मैं अभी देखा, जो अभी मेरा C2 था, वो भी हो सकता है, कुछ और भी हो सकता है। सो अब मुझे इसको इंक्लूड करना ताकि ये सॉर्टेड हो जाए। एक एरे में करेंगे तब तो ये इंसर्शन सॉर्ट टाइप का कुछ करेगा। इंसर्शन सॉर्ट में जैसे होता है लॉग एम टाइम में हम कर सकते हैं, इंसर्शन सॉर्ट में बाइनरी सर्च कर सकते हैं, बट इन ऑर्डर टू शिफ्ट ऑल द एलिमेंट्स वी हैव टू proceed towards order m kind of an approach, right? So definitely this kind of array like thing won't work. But if we think about some binary search kind of a structure or binary search tree में वो story ऐसे करता है, it stores in such a manner that when you go to a node, you know whether you should go to the left or to the right. So अगर binary search tree थोड़ा balanced हुआ तो हम क्या कह सकते हैं, ये जो सर्चिंग द बेस्ट एलिमेंट है ये हमको मैक्सिमम लॉग एन हाइट तक ही जाना पड़ेगा नीचे, या फिर लॉग एम कह सकते हैं, राइट? अगर ये बैलेंस्ड हुआ, बैलेंस्ड मीन्स द हाइट इज गोइंग टू बी लेस देन इक्वल टू log m or twice log m, whatever. This is balanced, means there is no great difference between one subtree and another subtree in a raw manner, right? So this is one such idea. We can use a BBST. ओके, वी कैन यूज अ बीपीएसटी टू से कि जब हमने ये प्रेफिक्सेस कैलकुलेट कर लिया तब मैं क्या करूँगा कि जब मुझे C2 के लिए अपना पुराना कुछ अच्छा प्रेफिक्स ढूंढना पड़ रहा है, मैं अपने पुराने सारे प्रेफिक्सेस को एक बीपीएसटी में देखना चाहता हूँ, एंड देन आई वांट टू सी विच इज़ द बेस्ट वन फॉर C2. व्हाट कैन आई से कि मुझे इससे कम एक चाहिए, मुझे चाहिए ओके इससे ज़्यादा मुझे एक चाहिए, प्रीफिक्स सम ऑफ C2 माइनस के, इससे ज़्यादा मुझे एक चाहिए बट जस्ट ग्रेटर और ग्रेटर देन इक्वल, ऐसा मुझे एक एलिमेंट चाहिए कि जो जस्ट ग्रेटर और इक्वल हो, तो मुझे लॉग एन टाइम में मिल जाएगा। अब मैं क्या कह सकता हूँ, मिल तो जाएगा, तो पहले भी मिल रहा था। कैन वी इंट्रोड्यूस अ नोड इन अ BST इन शॉर्ट टाइम? यस, इन अ बैलेंस्ड बाइनरी सर्च ट्री every operation whether you talk about red black tree or AVL tree, insertion occurs in order log n time. Suppose that n elements are there. Deletion occurs in log n time, और डिलीशन में आपका एक्सेस वो भी आता है, सो मैं एक्सेस अलग से लिख रहा हूँ। एक्सेसिंग सर्टेन नोड या फिर फाइंडिंग, मे बी फाइंडिंग सर्टेन नोड, वो लेता है ऑर्डर लॉग एन टाइम, ठीक है? तो ये सारा नोड, फाइंडिंग इज सर्चिंग सर्टेन नोड, वी कैन ऑल्सो से सर्च, सो एवरीथिंग टेक्स लॉग एन टाइम। सो यू कैन चेक दैट ओवर हियर इट इज क्वाइट सुटेबल टू आवर पर्पस। हम क्या कहेंगे कि हर एक, जब तुमने रो फिक्स कर लिया है, तुम दाएं की तरफ जाओ, तुम एक पर्टिकुलर कॉलम में जब पहुंचोगे, इसके पीछे वाले कॉलम्स को, उनके प्रीफिक्स सम्स को देखो और ये देखो कि कौन सा तुम्हें बेस्ट डिफरेंस देगा, विच कैन एक्चुअली गिव समथिंग लाइक दिस, that particular value whichever you have stored that has to be greater than equal to prefix of C2 minus k. We know prefix of C2, we know k, तो दिस इज द कांस्टेंट फॉर अस करेंटली। फिर हम प्रीफिक्स C2 को भर देंगे अंदर, फिर हम प्रीफिक्स नेक्स्ट वाले जो भी C2 डैश या जो भी होगा नेक्स्ट कॉलम, उसको लेके चालू करेंगे। सो व्हाट कैन वी से, हर एक कॉलम के लिए ये चीज़ करेंगे, हर एक के लिए लॉग ऑपरेशन है। सो हमारा C log C में हो जा रहा है, मेक सेंस। और हम लोग क्या यूज़ कर रहे हैं, सम बैलेंस्ड बाइनरी सर्च ट्री जो हमें C++ जावा ये सब प्रोवाइड करते हैं। जावा प्रोवाइड्स in the manner of tree set. C++ provides in the manner of which one? सेट, राइट? ऑर्डर्ड सेट, उसको सेट कहते हैं, ऑर्डर से जो कि अनऑर्डर्ड नहीं होता है, राइट? सो कूल, पाइथन में भी आपके होते हैं, यू कैन चेक, you'll be getting definitely all these things. So these things we can use and we can directly solve. Now if, like, it often happens that the interviewer wants to say, do you know how to implement a tree set, and you say that no, not exactly. So in that case, how can you solve it? Like if the interviewer says that please don't use those libraries, solve it in some other manner, or tell me, no need to solve now, tell me what is another idea of solving it so that you don't use such libraries directly, implement it from scratch. So in such a case, there are certain other implementations as well. अच्छा, इधर के लिए we are maintaining the prefix sums. Do we need to form all these prefix sums? जो हमने इधर फॉर्म किया था, सारा prefix sum क्या ज़रूरी है? देख लेते हैं. सपोज हम ये R1 R2 चालू कर रहे हैं. R1 R2 के लिए जब चालू कर रहे हैं, तब क्या ये हमें सारे वैल्यूज प्लस करने पड़ेंगे? Do we have to add all these values for the first column? If we have to add all these values, then additionally there is a cost of नंबर ऑफ रोज, राइट? उतने सारे रोज हर बार हमें जैसे ही हम मूव कर रहे हैं, हर एक कॉलम में हमें उतने सारे रोज ऐड करने पड़ रहे हैं. बट द थिंग इज, हमने तो डीपी का अप्रोच देख लिया है, उतना तो हम लोग ऑप्टिमाइज कर सकते हैं. इज देयर एन अप्रोच विच इज ईजियर? डीपी से तो हमें पता है कि ठीक है, अब तो वो करना बेवकूफ़ी है. अब तो अगर हमें फिर से हर एक करके कैलकुलेट करना पड़े और इसको अगर हम आर क्यूब आर टू द पावर 4 तक लेके चले जाए, दैट इज गोइंग टू बी सम नॉनसेंस. So we can optimize it using DP, but the problem of using DP for this prefix sums, the problem of using DP for those 2D prefix sums, जो DP हमने इधर फॉर्म किया था, ये सब DP, ये हो जाएगा एक्स्ट्रा स्पेस, ये हमारा ले लेगा एक्स्ट्रा स्पेस, राइट? ये हम क्या कह सकते हैं कि जब एक पर्टिकुलर R1 से R2 तक देख रहे हैं, हम एक पर्टिकुलर 1D प्रेफिक्स सम का एरे मेंटेन कर सकते हैं. जब R2 चेंज हो जाएगा, R1 चेंज हो जाएगा, हम उसी प्रेफिक्स सम के एरे को रीयूज कर लेंगे, उसको खाली करके रीयूज कर लेंगे, तो हमारा टोटल मतलब स्पेस इस प्रेफिक्स सम के लिए जा रहा है बस ऑर्डर m, नॉट मोर देन दैट. We are not spending time more than order m, or we are not spending an extra space more than order m. But if we choose something like DP, then we are actually spending a lot of space. We should not choose that actually. Like, this is another thing that interviewer might look at how you're approaching it, how you're implementing it, and how much your implementation is close to the best solution. And these are actually the metrics and the parameters on the basis of which your solution is going to be compared with the solutions that are known to the interviewer. Okay, fair enough. Let me check whether it is getting recorded. Yeah, okay. तो सोचिए कि हम लोग डीपी को कैसे छोड़ सकते हैं. हाउ कैन वी अवॉइड दिस? थिंक अबाउट इट. इसके बहुत सारे अप्रोचेस हैं, एंड आई वुड एनकरेज यू कि आप एक अप्रोच सोच लीजिए. व्हाट आई वांट इज कि आपको ऐसा कुछ निकालना है, हर एक R1 R2 के लिए आपको ऐसा कुछ निकालना है, एंड आई वांट दैट दिस एंटायर थिंग टू हैपन इन ऑर्डर वन टाइम. ये ऐसा नहीं कि समेशन ये होता रह जाए, ये ऑर्डर वन टाइम में. अब आप चैंपियन है, आप कह सकते हैं कि ठीक है, प्रीफिक्स ऑफ j you can define in terms of prefix of j minus 1. Prefix of j you can define like this. Prefix of j is equal to prefix of j minus 1 plus करंट जो कॉलम है प्लस करंट कॉलम का सम. करंट कॉलम का सम क्या होगा? ये करंट कॉलम निकालने में हमें ऑर्डर n लग जाएगा. मेक सेंस? ऑर्डर n लग जाएगा वो पूरे रोज सम अप करने में, राइट? तो हम कह सकते हैं कि इसको हमें अवॉइड करना, इसको हमें ऑर्डर 1 में ले आना है. हाउ कैन वी डू इट? ये हमें नहीं करना है, ऑर्डर n नहीं चाहिए. तो ये जो कंप्यूटेशन हो रहा है, ये ऑर्डर 1 टाइम में आ जाना चाहिए प्रीफिक्स ऑफ j के पास. हमने देख लिया प्रीफिक्स ऑफ j माइनस 1 को यूज करेंगे तो पुराने सारे कॉलम्स को हमने देख लिया, लाइक वो सारा ऐड करके आ जाएगा, बस इनको ही ऐड करना है. इसके लिए भी आप यूज कर सकते हैं कि वो आपके कॉलम के प्रीफिक्स फिर से वो डीपी चीज़ यूज़ कर सकते हैं. बट व्हाट आई एम सेइंग इज कि डीपी वाले जो 2D चीज़ें हमने किया था उसको थोड़ा अवॉइड कीजिए, क्योंकि बहुत एक्स्ट्रा स्पेस था, उसको थोड़ा अवॉइड कीजिए. बट अगेन प्रिवेंट दिस फ्रॉम हैपनिंग. We can say something like this. Let us see what is the best thing that we can do. We can say कि हमारा पहली बार हम लेते हैं R1 के लिए, R1 से लेकर R1 तक, बस यही कंसिडर करते कि एक ही रो रहेगा. हमने सारे के लिए प्रीफिक्स सम क्या निकाल लिया? इस रो का जो प्रीफिक्स सम होगा वही अपना आंसर होगा, राइट? इस रो का जो प्रीफिक्स सम होगा वही अपना आंसर होगा. सो हमने सबके लिए प्रीफिक्स सम निकाल लिया। नेक्स्ट हमें जब R1 से R1+1 के लिए निकालना है, हम क्या करेंगे? हम ऐसा कुछ कह सकते हैं कि यहाँ से ले लो नेक्स्ट वालों को और ऐसा कुछ कर दो कि R1+1 में जो भी वैल्यूज तुम्हें मिल रहे हैं वो तुम इसके साथ ऐड करो। फिर इसमें क्या करेंगे? इसमें इस वैल्यू को जब ऐड करेंगे प्रीफिक्स सम में, तो इसके पास ऑलरेडी प्रीफिक्स सम सेव्ड है यहाँ तक। हम क्या कर सकते हैं? हम ऐसा कुछ कर सकते हैं कि how can we now form this new prefix sum? Okay, we can do something like this. कि ये पर्टिकुलर सारे सम्स हम लोग ऐसे स्टोर करते जाएंगे, ठीक है, और प्रीफिक्स सम हम लोग बाद में लेंगे। तो ऐसे हम कुछ करेंगे कि पहले ये सारे अपने अपने वैल्यू स्टोर करेंगे और फिर जैसे हम नीचे जाएंगे हम ये सम लेते जाएंगे, ऊपर में जो सम है उसके साथ सम ले लेंगे। विल टेक दैट सम, विल टेक दिस सम, विल टेक दिस सम एंड सो ऑन। नाउ व्हाट कैन वी से? वी कैन फॉर्म द प्रीफिक्स सेट इन ऑर्डर सी टाइम, राइट? फिर नेक्स्ट क्या करेंगे? ऑर्डर सी और ऑर्डर एम। फिर नेक्स्ट क्या करेंगे कि यहाँ से यहाँ तक वापस ये कैलकुलेट कर लेंगे, सारे के सारे जस्ट एक वैल्यू ऐड करना है, नीचे सब ऐड करना है और फिर से हम प्रीफिक्स हम ले लेंगे। तो कितना हो जाएगा? ये कितना स्टेप्स ले रहा है? ये हर एक के लिए बस एक स्टेप ले रहा है। सो दिस इज ऑल्सो ऑर्डर एम एंड देन व्हेन वी विल डू द प्रीफिक्स सम दिस इज ऑल्सो ऑर्डर एम। सो जब हम एक एक रो ऐसे ऐड कर रहे हैं, हम क्या बोल रहे हैं? पहले देखो दिस इज रोज। हम पहले देखेंगे रोज 1 to 1, 1 to 2, 1 to 3, 1 to 4 ऐसा करके, ठीक है, 1 to 5। तो हम कहेंगे कि जब रो 1 1 से रो 1 2 में आएंगे हमें बस इतनी ही चीज़ें करना है, बस इतने सारे एडिशंस करना है और फिर लेफ्ट टू राइट एक प्रीफिक्स हम करना है। फिर जब 1 2 से 1 3 में आएंगे हमें ये सब ऐड करना है, फिर ऐसे ऐड करना है, ऐसे ऐड करना है एंड सो ऑन। फिर हम कहेंगे नेक्स्ट हमें 1 को छोड़ना है, हमें 2 से चालू करना है। तुम डायरेक्टली 2 से चालू कर सकते हो। आप सोच सकते हैं ठीक है 1 5 से हम लोग वो 1 को हटाते हैं ताकि हमें 2 5 मिल जाए, ऐसे भी आप कर सकते हो। आप यू कैन चूज एनीथिंग। बट इन 2 2 व्हाट इज द टाइम टेकन? फ्रॉम ओनली 2 to 2 again order m time. Then from 2 to 3 you just have to add the third row. Then 2 to 4 you just have to add the fourth row and so on. So like this we will get all the NC2 possibilities and we can compute them. We can actually find all these prefix sum values for every such row combination in order m time. When we find this, after that we can do that reset operation. It is done, right? That's it. So definitely as a maybe easy precursor to this problem, you can first think of the problem that it is a 1D array, and now what is the maximum subarray that you can, or what is the subarray that you can choose which will have the maximum sum less than equal to k. So this is the easier version of the problem, easier version, okay, which is given a 1D array, given a 1D array, find the subarray with max sum less than equal to k. Okay, you can solve this question using such constraints and you can see how we can solve this. Suppose you have length n, so you can see how we can solve this in n log n time. Quite similar. Okay, order n log n time. We can use the same approach. As we are proceeding forward, we are getting a prefix sum. Now for that prefix sum, we can check what is the best precursor in terms of the prefix sum or in terms of the previous prefix sum that we can subtract and get the best value less than equal to k. We can again do the same thing. Can there be any other approach? Definitely there can be other approaches, but let us first code this problem. Let us first code this solution that we discussed to check that, okay, one approach is working or not. So fine, let us solve the 2D version only. So let us CP combination sum. I'll be copying this to what is the question? Maximum sum of rectangle with at most sum at most k. Max sum rect at most k. Okay, CVP. Now, okay, I'll remove all these things. We'll have int main. Just a second. Okay, now what shall we do? We will first take that as input. So we have n rows, m columns, and maybe we can use ll. Okay, int k is also there. So c in n m k. Okay, and now we'll be forming something like this vector. I think vector ll, and we can have the input matrix, I can say. So it is nothing but n comma vector ll m comma 0, right? And for ll, or maybe yeah, int I equals 0, I less than I plus plus. For j equals to 0, j less than j plus plus, j less than m j plus plus. I'm using such short variables. You can name this as row and column. It sends a better impression to the interviewer. Okay, so we will take this in mat of ij. Now what next? Okay, now what I'll say is I'll be keeping a sub procedure which will calculate to me for all these prefixes. So I can do something like this for all the row 1, R1. I'll start from 1, R1 can go up to n, and R1 shall increase by 1. For int C1 equals 0, C2, okay, let us name it as C, right? C is less than M, C plus plus. Now let us see what we'll be forming. We'll form something like this. After this we need to choose R2. R2 equals to 0, R2 less than equal to n, less than n, and R2 plus plus. Now we'll say before we get inside R2, we have to form where we will store all those prefixes or whatever we store. First, what did we discuss? First we will do this. First we will store the values. So observe very carefully what I'm going to do. I'm going to say, okay, first form the values as m things which are having just zeros, nothing else. Okay, and I'll take R2 from R1. Okay, I'll take R2 from R1. So what shall I say? Whatever is my R2, I'm going to add that. So I will say that, okay, go on adding this. Val C equals to, we can say if C equals to 0, then we will just mention as, or I'm sorry, okay, so it will be something like val C plus yeah, mat of R2 C. Does it make sense? Okay, now we are getting all the correct values that we are checking up to this particular server, so we are getting the correct totaling. First time when we are doing only for R1 to R1 only, we'll get all the values basically in that single row. Whatever values are there, we are going to get everything. And now we can say that after that we'll be plussing everything, and then we can say, okay, now let's form some prefix sum. Let us form some prefix sum. Prefix sum m0, prefix c equals to, if c is 0, then just store val c, else you have to store val c plus prefix of c minus 1. Makes sense? Okay. Next, what can we use? We can do something like this. Okay, so we have got these prefixes. When we have got these prefixes, now we can say, okay, for this particular row range, whatever we had to do, we have done. Now we have to call the function to calculate best answer. You can say best answer or best sum. You can say. And what are we going to pass? Let us create it. LL calculate best sum, and we are going to take these things. Okay, so we have got value, we have got prefix. Yeah, so val, let us form over here only. We are going to pass the number of columns, which is basically the size of that vector. We are going to pass prefix. That's it. Okay, and we can say we will find, suppose LLANS equals to 0, or we can say it is mat of what can we say? Okay, let us make it 0. Let us imagine that at least one such rectangle exists. Okay, so ANS is 0, and suppose k is greater than 0. Okay, ANS is 0, and what can we say? That okay, ANS equals to max of ANS comma. So whatever is the best thing that we'll be getting, and we'll for from the max with that. Next, what can we say? Okay, here we'll be basically storing this m prefix. Yeah, that's sufficient. You have LLM, you have vector LL and prefix. Now we know something, that in set there are certain functions which we need to depend on. I will be searching all those things because I don't remember them. I less than m and I plus plus. We will initialize a set for it. Set LL S. That's it. So we have seen we have to find out something like this. Basically, the we can say it is something like the ceiling, that the value just greater than or equal to this. So let us see what we have. Set upper bound and lower bound C++. Let us see what we have got. Okay, lower bound, what it does is it performs exactly what we want. So it says that for a certain value, it will check whether that is present, otherwise immediate next element, which is greater than k. So this is exactly what we want. So we will pass this particular thing, pre of c2 minus k. So let us see when we pass it what happens. If prefix or maybe set dot find prefix of I minus, okay, k I need to send. So suppose I send k over here, and we'll get LLK over here, LLK. So if this minus k is going to be not equal to s dot end. S dot end means you have not found anything, and not equal to s dot end means you are finding something. Then you can say, okay, LLANS equals to 0, and I'll be storing ANS equals to max value possible, ANS comma s dot find prefix I minus k. I don't know what is the return type. Let's check what is the return type. Return value returns an iterator. So how do we get the value of that iterator? Star. Okay, so we'll get some iterator. We can print star over here, star of this. That should suffice. Okay, so we are getting this, and now we can return it. But we are forgetting some. Okay, we return ANS, and we are forgetting something. That is, we must store this set dot insert. Insert. What is that? Prefix I. Prefix I we have to insert. Makes sense? Okay. Now we can just print the answer, and let us check. G plus plus max sum at most k. J, I am not defining them. Int. Okay, let's check now. Okay, dot slash a dot out. Let us take some 3 cross 4. Okay, or maybe again 2 cross 4, the way we were choosing, and we will take a sum of suppose 14. We will choose 5 minus 3 2 4, and we'll have 3 minus, or suppose 3 3 minus 2 8. Okay, so we are getting 0, we are not getting the correct answer. That is strange. Let us print whatever we are getting inside this prefix I. Because we can easily see that the answer should be better than that, right? Better than 0. So we are getting a lot of things. S dot find, it is not equal to S dot end. Yeah, it's fine, at least to me. Max, let us check whether it is entering here. S dot find star of S dot find. Okay, endl. So let me see if anything is getting entered here. Suppose for this, let us now check. Again, same input I'll be seeing. Okay, nothing is actually getting printed, so it is not entering over here. So if we search it, something like s dot find prefix I minus k. I am not sure if it is able to print an iterator. Maybe it is not able, right? So star. Okay, I'm sorry. So it should have been the lower bound, right? I was doing find. I'm sorry. That's my error. We have to do lower bound, right? Lower bound. Now this should suffice. Let's see. Again, it is 0. So over here, maybe it is lower bound. That is the reason. Over here only it needs to be changed. In place of this find, it needs to be lower bound. You have 8. So, but we can say 8 plus 4 is also possible. 8 plus 4 should have been possible. So let us see what are the things we are sending. Let us check that. Cout prefix of C endl, right? Okay, maybe we can do something. What we can say is that initially our value is going to be 0. So we are going to send something and like this. So prefix of C is equal to something like this. So initially, if I don't take any row, any column, then it is going to be 0. From there, if I see, I'll get the entire thing. I should get a greater opportunity. But anyway, still then, like taking this 8 4 should have been available. In fact, taking this entire part 8 4 should have been available, which is 12. Because I'm printing just the complementary things. But anyway, m plus 1 over here, I can do m plus 1, and let's now check. Okay, just a second. We are getting some value. Basically, it should be prefix of I minus this, right? It should be prefix of I minus this. Prefix of I minus this is going to be less than equal to k. Right. Now I think we can maybe try compiling it once again. Yeah, I'm getting 12 now. So let us check. I'll now change this to, um, let me change it to 414, and I'll do something like this: 5 minus 3 2 4, and I'll be changing this 3. Suppose I make 8 over here, and then I'll choose something such that it becomes 13. So let us choose. We have minus 3 minus 1 3 11. For 13, uh, from 11 I'll require minus 6 and 8, then I should get 13. Yeah, we are getting 13. Okay, so what have I done over here? What I basically was slightly missed was that, say, this is the best value of pre C1, but with that best value what should we do? Our answer is going to be what? It is going to be pre of C2 minus pre of C1. So I just did that thing, that whatever value I'm getting from lower bound, I'm going to subtract that from this current value. Make sense? I'm going to subtract that from this current value. Pre of C2, that is exactly what I'm doing over here. That prefix of I minus this thing. Okay. And yeah, this thing was also important. What I did was, initially I did not take this 0 column. Why this is important? Because if I want to take all the columns up to there, I should have some difference 0 behind it, so that I can subtract the entire thing. So that's it. I hope the basic idea is clear, and see, the implementation was short enough. We have completed in like 44 lines of code, and leaving the first few lines and leaving all these things, maybe the actual code is around 30 lines, right? If you leave the inputs and everything, or maybe 25, like whatever. So the number of lines of the actual code is quite small. So this is something that you can keep in mind. You can solve the easier version of the problem. It will simply be that you don't need this R1 and R2. You just need this part. For the simpler version, which is 1D array, you have to find the maximum sum at most k. For any sub array, you basically need to choose something like this. You need to do something like this. That's it. Okay. So that's it. What is the time complexity? See, within this loop, this for loop is only taking the time. Okay, this is order m, and this is order n into m. How? Within this n, first we are forming a vector of size m, then we are doing order m operations, and then we are calculating something where order m log n is taking place, m log m. So it is basically m log m inside this. So this is n into m log m, and this is again n, so it is n square m log m. Okay, so the time complexity that we are reaching is, the time complexity that we reached in this problem is order n square m log m. And you can say, okay, if n is greater and m is smaller, then this is quite good. Sorry, if n is greater and m is smaller, we can do the other thing. We can do the other thing, that is m square n log n. So this is often written as order min of n comma m square multiplied by max of n comma m multiplied by log of max of n comma m. Does it make sense? Okay, so that is exactly how we actually find the best answer. Another approach, something that I was touching upon, is what if the interviewer asks you what can be another way of solving it? You can solve it using merge sort. How? You know all these values are going to come. You already have these values. You have all the values of prefix values. I'm going to write it like this: P1, P2. You have all these values: P3, P4, P5 up to Pn. Using merge sort, you can actually find out for every element what is the best element in that manner. How? See, when we do merge sort, you must understand that there is a particular step where any two values get combined into one subarray. So before a particular step, what happens? Like, think about the combination step. So every pair, any pair, P3 and P5, it can happen like this, that P3 might be over here. It definitely must be in the left half, and P5 should be in the right half before combining. It must be, right? And after combining, it might happen that P5 may come here, P3 may come here, whatever. But at this stage, whenever we are combining, we can check this. Why? Because we know that the previous part is sorted. We know that this part is sorted. We know that this part is sorted. So using all these values, we can calculate the best value over here, and we can actually do that in order n time. How? We can actually say that, okay, this is the value. Suppose we have something like this: 1, 5, 12, 19. Okay, this is my first value. This is my first array, and this is my second part, second half, which I am going to combine with this, which is having some values like 14, 17, 40, 50. Okay, something like this. Now from here, what can I say? Suppose I require a target. My target is, or rather this k, the value of k, this is something like, just a second, let it be something like 14. Okay, so from these examples I know that the best thing I can obtain is 17 minus 5, 12. That is the best I can obtain. Okay, sorry, 14 minus 1 is 13. So let us make it maybe, let us make it 12. Okay, let us make it 12 to make the example more interesting. Okay, so now we have 12 minus 5 is smaller, and okay, so this is forming the best pair. Now observe it. When we'll be combining it, we will say that for this particular, um, yeah, for this particular node, if this node is quite small, then just go ahead. Find me the node which is just greater than this element plus k. So this element plus k is 15. This is just greater than 15. So I will say 17 minus 1. 17 minus 1, okay, this is one pair that we get. 1 and 17. Okay, I have to choose, okay, I'm sorry. We have to choose at most 16, right? At most 14. So we will say, okay, I have 12 minus 1. I have 12 minus 1. So I can say, okay, I'm going to have 12 minus 1. But then automatically my desire will rise. I know from 5 and 12, I will get something which is much lesser, right? But I need to maximize it. I need to maximize it. I know that this will stay below 14, but I need to maximize it. So definitely, I will say that when 1 and 12 have satisfied, 5 and 12 are also going to satisfy. And so let me check for something else. Let me check for 1 and 17. So I will check for 1 and 17. When I check for 1 and 17, I see that it is 16, which is greater than this. So it is not obeying this. So what can I say? If I proceed this pointer further from here, then the values will rise even more and I will not get any benefit. So I can say, okay, there is no reason to go forward. Let us do something like this. Let us move this one forward. So we won't move that one forward. We will move this one forward. Now 5 and 17 I'll be comparing, and I'll be getting 5 and 17, right? And this is a good one. This is giving me 12 as the value, 12 as a difference. Then what can I say? Okay, I'm getting 12. Now, which one should I change? 5 or 17? I know if I change 5, then of course with 12 and 17 I'll get something less than equal to 14, but that will be lesser. I want to maximize it. So I should not change it. I should not change it at this step. I should change this one. So we will check with 5 and 40. This is greater. Since this is two greater, I know with 5 and 50 this is just, there's no meaning of checking this. So I will check for 12 and 40. With 12 and 40 I'll see again it is greater than 19 and 40. So with this I'm actually saying that, okay, we have compared all the left half of the array elements with the right half of the array elements. And in this way, at some part of the other, you will see that any two elements, if you have to compare, you will get it compared, or at least you will find them in the two halves. If they are skipped, that essentially means that that is not important. So in this way, you can see here the sortedness has been exploited by the iteration of merge sort. Now after this, what merge sort is going to do? It is going to combine this. It is going to combine this in order n. And after combining this, it will like again call it. So again, it is going to send to its parent. Over there also same kind of combination is going to happen. Same kind of combining step. So does it make sense? This is slightly, sometimes slightly harder to implement, but I would encourage you to practice this because it is quite easy to implement. You can see, like from here, you can implement this if you practice on it. What you basically need to do is, one, you know what is basic merge sort. In a basic merge sort step, you need to call merge sort on the smaller halves, call merge sort on the two smaller halves, then you need to combine. Before combining, Before combining, need to do just one step, and that single step is going to be nothing but find the best. Find the best. If you find that ever you are getting k, exactly k, that means k is going to be the answer. If you get the sum exactly equal to k, then k is going to be the answer. So just return k. Don't do anything else. Okay? Otherwise, this is exactly going to give you like find best every time when you find the best. And remember, you should not suddenly, see, this step is also taking order n time. Don't forget. So we are not affecting the asymptotic time complexity of merge sort. We are not making it go up to n square. So we are relying on merge sort, and within merge sort we are using it. Why are we able to use it? Because every pair of elements at some point of the time in the merge sort appears in two different subarrays before being joined. Okay. So that is the reason that is the verifier that we are exploiting over here. There are many other approaches. If you want me just to mention it, then another approach is about segment trees. Segment trees, what I can say is that, okay, you have all these elements, you are going from left to right. Now what you will do, you will store this in the segment tree. You will first store this in the segment tree, then you store this in the segment tree, and every time you will say, whenever I get this element, what is the best element? Suppose this element is x. So I will say my previous element need to be less than equal to x minus k. So let me find out. Now you have to do just a range query. So you have to do just a point update and a range query. Point update, you can maintain a kind of, max segment tree maybe. Yeah. You have to form a max kind of a segment tree. Then you can rely on a range query. So it will be simple. Simple point update and range query. Okay. Using that you can calculate, but the only important thing is that if AI becomes large, if AI is suppose less than equal to 100, then using segment tree is doable. But if AI is suppose greater than 1000, suppose it is greater than 1000, then the total time complexity will become how much? It will actually become n square m log of the size of this, like this. So it is a max. Okay. So whatever a max is. So suppose it is something like suppose the values are very large. Okay. So n square m is taking us to 10 to the power 6. Now say a max. Okay, this is only the time complexity, but actually the space complexity you have to think about whenever you solve for segment trees. The space complexity for segment trees, just simple, segment tree space complexity is going to be order a max. Okay, if you have to store using these values, we can improve it if we know that there are at most how many sums. If you know that the number of sums are limited, how many sums are there? Using the prefix sums, you have at most m sums. So if you want to, okay, say that, okay, I'll utilize this number of sums less than equal to 100 thing, then we can use two different things, coordinate compression, you can use this, or we can use sparse segment trees, either is going to help you. Okay, but these are much harder than the question demands. Okay, these are some harder concepts which you can apply, and you can see they will help you to find the solution because there are 100 values, so definitely, and this is basically range query. But there's a particular kind of range query which actually merge sort actually helps in solving very easily, and they're not online, they are offline. So that's it, I think. Yeah, if they're online queries, then you have to rely on this coordinate compression, not coordinate compression, you have to rely on sparse segment trees. But coordinate compression actually helps you, like if in this kind of a case you can use coordinate compression, but it will become harder than your current problem is. But if it is less than equal to 100, you can use normal segment tree also. Here it will be log 100, and there it will be like the size of the segment tree will be 400. Okay, so the size of the segment tree is usually less than equal to 4n. According to like the implementations that we mainly use in computer programming, it is less than equal to 4n. If you maintain sparse, there also you can follow the array implementations. But anyway, let us not proceed much deeper into segment trees. I hope if you have some interest, then I hope you can draw the relation. We are basically doing range queries. How we are doing range queries? We are going to say, suppose we have got something like this, 2, 3, 8, okay, something like this, or maybe 7 and then 9. For 9, which is the best predecessor? So I know for 9, suppose up to 5. Up to 5 I can have elements. So I'll search in the segment tree what is the best value up to 5. It will return me 3. Okay, in that manner I'm going to get the answer. So maybe in some other session you can tell me if you want me to describe on this or maybe related problems, how we solve using segment keyword, particularly this merge sort method. If you want the implementations of this method, then you can let me know. And yeah, that's it. uh, I hope you have understood this problem, and I hope if asked then you can answer this problem well. So yeah, that's great. So take care, keep coding, try to implement this on your own so that you gain a better clarity on this, and try to implement using the approaches that I haven't used for coding. Try to implement these approaches. Okay, that's it. So uh, good day and good luck with all your interviews. Take care. Bye.